Hi, I'm going to talk about one-dimensional vectors and geometric transformations for them. And this is supposed to be an introduction, a stepping stone for concepts and ideas that later on can be applied on 3D vectors and 3D transformations. Just it's much easier to talk about them in this simpler context. But keep in mind, of course, you still have to dominate and be able to manipulate quite well scalar values, because even though many times you're dealing with something interesting with 3D vectors, a lot of times the control values are scalars, or you're going to decompose your vectors into scalars. So it's very important to be able to dominate scalars. Okay, so instead of thinking about values, scalar values like -3, 4, 1, 0, etc., just as something in abstraction, I can think about them as a position on a number line. And with those positions, I can start to have geometric constructs like points, lines, vectors, etc. So a vector is a geometric construct that has a length and a direction, and can also be defined by 2 points. And the vectors that I'm going to talk about are position vectors. They have the characteristic is that the tail point is bound to the origin. So let's look into a coordinate system. So I have here a line, and to have my coordinate system on it, I have to have a reference unit vector. This little vector, it's a unit vector, which means that it has length 1. This little reference vector, it's basically going to dictate what other vectors are. So it gives me 3 things. It gives me the origin, it gives me the length of 1 unit, and it tells me what's the positive direction, and by that also what's the negative direction. So with that, I can have the other coordinates. And so basically here, for example, in Lightwave, if I put this arrow unit vector up, you can see that this is my little reference unit vector. And if I change it, my number line also changes. If I scale it, etc. So this basically defines what other vectors are. So in this case, you see these vectors, the position, the absolute position is the same, but the values they have on the number line changes depending on, what do I do to my my unit vector here. So okay, have my coordinate system, and so instead of looking at -3 as just an abstract value, I can think about it position -3. But moreover, I can think about the vector that goes from 0 to -3. And so now it's not just a single a value in the ether, but it's defined a vector, has a length, has a direction, and this is because we're dealing with position vectors that have the tail bound to the origin. So the tail point, in this case, I'm dealing with scalars, is always 0. So I'm left with defining the position of the head. Of course, with 3D vectors, we're going to see that the origin will be 0, 0, 0, and the head point will be defined by 3 channels, x, y, and z. So -3 can define this vector, 4 can define this vector, etc. The only special case here will be 0, because a vector that goes from 0 to 0 has no length and has no direction, because 0 is neither negative or positive. And so this can be a little bit problematic, and sometimes you gotta check for this case. But for now, let's look into the transformations we have here. So here I have this object called result. Let me hide this little unit vector. And I have this object called results, and in it, there's in the motion panel, and I have this item motion node editor. This was the first node editor that we had that allows to change motion channels through nodes. It was done by Denis Pontonnier, and still very useful today because it has exposed individual scalar channels. And this allows me to constrain only the channels that I need, instead of having to plug in composite channels into position, rotation, and scaling. So I still use it because of that. It's very handy. And in here, I have this compound called transform 1D that I'm going to use to drive the conversation about the transformation. So in it, I have 3 basic transformations: scaling, translation, and reflection. Translation is basically position. I'm just calling it translation because to me it sounds more like a transformation than a position, a coordinate, a location property, but it's the same thing. And so here I have this input scalar value, and in this case, since I turn on input pi, I can see that it is 2, and I'm going to scale it by, say, 2 times by changing this one to 2 and plug in here. So it goes from 2 to 4, and I'm going to translate it by 1. So it goes from 4 to 5, and then I'm going to reflect it. And when I reflect it, you'll see that jumps from +5 to -5. Okay, so these are the basic 3 transformations. In this section, I'm just going to look into the most basic one, which is the reflection. So reflection has to deal with the sign, or the direction of the vector. So if I have, let's say that I have here let's see, 2 and -2. So they both have a length 2 or magnitude 2, but this one is positive and this one is negative. And so sine, it's going to keep this, but it's going to change this. So it can have something with the same magnitude, but it can be either either positive or negative. And that's basically between those two that the sine, the reflection here is going to do. And the node used for it is called sine. And if I just plug it in here, let's say I have 2, and now out it comes the value -2. If I change this to -2, out it comes +2. So sine node basically turns positive into negative and negative into positive. Then we have the absolute node, or in short, abs. And the absolute node is basically going to return me the positive, always the positive value. So here I have a negative value, it gives me a positive value. And if I put here 2, it's still going to return 2. So, and here, let's say abs, it's going to, from positive, I'll get positive, and from negative, I also get positive. And so what these are doing different things. This one is changing, if you look into these as vectors, this one is changing the direction. And this one is basically giving me the magnitude or length. So it's returning the magnitude. Now there's a last one. It's called copy sine. And copy sine basically has 2 inputs, as you see. And so copy sine splits the, let's look into what it does first about the value. So here I have the value 2, and I'm going to plug it here in, and then I'm going to have another node. And in this node, this scalar node, I'm going to put, let's say, a negative value, say -999. And so I'm going to plug it in here. So I started with a value of 2, and now I have a -2. That's because the second value, it's driving the sine of my value. So whatever I have in here, even if I, let's say, I'm going to put this here. Even if I, let's say, put a -2, I still get the same output, which is -2. Not because I've put -2 in here, but because this other value, it's driving the sine. So what this node actually does, copy, let me put it here, copies, copy sine. Yeah, my hand is a bit stubborn there. Okay, so what copy sine does, in a way, it splits the responsibility for the vector. So the first input, called in, it's going to control the magnitude or length. So it's going to be, let's say, I'm just going to put this red, and this is going to control the magnitude of the vector. And the other port, called sine, it's basically going to control the direction. So it's going to be this one here. So it's going to be either negative or positive. So it splits the responsibility. And this is very useful at times because you want to deal with one of them in isolation and then put back your values or recover some of these properties. And we can see that here in a quick example. I have this object here called instancer points. And in the instancer tab, I have this set up with 2001 instances. Basically, it's this number line that you see here. So if I hide it, you see that now those instances go away. And I'm going to open this up, and in the nodes tab, open the nodes. And so basically here I have a simple setup where I have an array of positions on the x-axis, 2001 positions. And if I plug the x position onto the y offset, I basically get a way to graph things. So in this case, I can see that, for example, this instance here has the same x value as its y value. So the input is equal to the output, and well, it checks what I have here. So this allows me to basically graph things, and I can see the input and output in a 2-dimensional style. So in this case, let's bring here the copy sine. And let's say that I want to basically graph the square root. And so there's a node here by Akira Asagi called squirt, and basically allows me to, if I plug this here and here, you can see that now I can see the graph for the square root. But you'll notice that the negative values are gone. This is because I cannot have the square root of -4, right? It's there. There's none. And so if I try to, let's say, put here -4, right? It's it's going to give me this error. This error means it's not a number, it's undefined. And when I have these, it basically invalidates my node tree. And in this case, for the instances, it basically makes them disappear. So let's say that I want to, I don't want negative numbers because I don't want, these instances to be invalidated. So I'm going to use an absolute node, scalar abs. And so with this, I only have positive values. Okay, so now I have my instances showing up again. There's no undefined error. Great. But when I look at it, I don't like the fact that they come up into the positive output values because, my positive values also come here and these were negative. So maybe I want them to go into the negative space. Well, for that, I can basically recover the sign they had by basically using my input as the sign in the copy sign and have the absolute square root to drive the length of the value. So if I come here, now I cheated my way into calculating the square root for negative values, but also have the result go into the negative. This is a simple example of breaking things into components and perform calculations separately. So in this case, I changed the magnitude of the value, but I did not change its direction. Next, I'm going to look into mapping, rescaling, functions, etc.